in the first section, we're going to be talking about systems of equations and matrices. This course deals primarily with those two subjects. So I want to start with the very basics, and the assumption is that you've solved some of these before in your life, and hopefully this will seem somewhat of a review. So let's take a look at a very simple system of equations that I'm sure you've seen in your life before. Now what I'm going to do is solve this, but I'm not going to solve it the way you probably are used to solving it. I'm going to solve it in a way that is, I guess, easiest to be compatible with this course. Let me just show you what I'm talking about. So here's what I do. Now you might remember the method of elimination, and that's primarily what I'm going to use here. What I'm going to do is I am going to focus here on these two guys, the 2x and the 5x. What I want to do is wipe out this entry right here, the 5x. So I'm not quite eliminating x like you think, but I'm going to, I guess, slim it down, make it easier to figure out what it is. Watch what I do. This and this will also give you some of an idea of the notation that we use. I use a little squiggle line, although I think your textbook doesn't use that. I'll try to do what your book does. I think they just use an arrow like this. And we refer to each equation as a row. So what I might do is this. I might say 5 times row 1. So that changes the first equation to the following. 10x minus 15y equals 40. And then the second equation, I'm going to multiply it by negative 2. That way I get negative 10x minus 8y equals negative 34. And the next step that I'm going to do is I'm going to add these two together. You, as I said, you may recognize this as the elimination method, but it's not exactly the elimination method, and you'll see why in a minute. So now I'm going to add row 1 to row 2. So what I do is I'll leave row 1 alone. I'm only adding it to row 2. So the first equation is untouched, and that's common here. We don't do anything with the first equation, or whatever equation we're using to do things to other equations. However, when I add the two rows together, look what happens. The 10x cancels with the negative 10x. The x's go away, but then over here I have negative 23y. And then 40 minus 34 is 6. And so I'm able to solve for y by dividing by negative 23. Now, the typical method right now is to divide by negative 23, get an answer for y, then substitute that back into the first equation and trying to determine what the x value is. And that's just to get an answer is fine, although it hides a little bit of the theory that we're trying to get to here. And it introduces a fraction, and working at least by hand with fractions is very clumsy. So I'm going to avoid that. Now, I'm not going to solve for y explicitly. What I'm going to do instead is I'm going to try to wipe out this item now. The negative 15y, I'm going to try to make it go away. So what I'll do is I'll multiply the first row by 23. And so that gives me 230x minus 345y. And then 40 times 23, I believe, is 920. And the second equation I can leave alone because you'll see what I'm going to do. Now I do know that the first equation is 15, I mean the 345 is 15 times 23. So what I'm going to do now is I'm going to take negative 15 times the second row, and I'm going to add it to the first row. So notice the 230x stays where it is. But if I do negative 15 times negative 23, that's positive 345. I'll have positive 345y plus the negative 345y, and that will zero that out. Now, when I take negative 15 times 6, I get negative 90. Negative 90 plus 920 is 830. And the second equation, notice now I'm easily able to get my answers. All I got to do on the first equation is divide it by 230. So for x is really easy. X is going to be 830 divided by 230, which I believe is just 83 over 23. And then y, if I divide by negative 23, I will get y equals negative 6 over 23. So I have my answers. In this course, we'll write our answer in the following format. It'll look like this. So when you write your answer, it's in what's called a vector format. So in fact, the items that we'll be dealing with quite often in this course will be vectors. And so let's go and take a look at this same problem, but I'm going to do it using something called matrix notation. Well, let me circle this. Let me have that equation back that I was using before. So 2x minus 3y equals 8. And the second equation was 5x plus 4y equals 17. So now I want to solve using matrices. So what do I mean by that? Well, take a look here. Matrix simply writes down the coefficients in the set of equations. So you can see where these are coming from. The 2 in front of the 2x's here, the 5 in front of the 5x's here. So this first column, if you will, is all the x's. And the second column, if you will, are the y's. So this is the coefficient. And in this course, there'll be plenty of times when we work with just the coefficient matrix, because sometimes the things that we want to know and understand are not necessarily related to whatever it equals. Sometimes we're looking for properties of the matrix itself. But in the case where we want to solve them, we will typically write something like this. So you can see now is you have the coefficient matrix as before, but then I've appended to it this column, this 817, which are the answers. And so this thing is called an augmented matrix. Now a lot of books, although not all of them, a lot of books will simply write something like this. They'll simply write 2, negative 3, 5, 4, 8, 17. And not put the little vertical line that I do. I personally have grown used to this, so I doubt I'm going to be able to change it to this notation. Even though this is a popular notation nowadays, I'm going to stick to this. No student has ever told me that dropping that line has made it impossible for them to understand what I'm doing. So anyways, I'm going to go through the same stuff I did before to solve this thing and get the same answer, but show you while I'm doing this some of the what they call row operations for a matrix. So here's what we do. Let me start it off. I have my 2, 5, negative 3, 4, vertical line, 8, 17. Now what I'm going to do is, like I said, I'm going to try to wipe out this number 5 down here. Now, if I multiply the first row by negative 2.5 and add it to this second row, I will wipe that out. However, it will start to introduce fractions. And whenever you're doing this stuff by hand, fractions will cause all sorts of problems. And even if you try to get the answer using a calculator, many times, even if they are capable of doing fractions, the computations are so extensive that many times the answer will be a rounded off answer that is not correct, even if it tries to use fractions. So you have to be careful. Although most of the time the calculator can give you the correct answer, but I wouldn't trust it. So what I'm going to do is try to make it compatible right here. So what I'm going to do first is I'm going to multiply the first row by 5 and then the second row by negative 2. That will give me a 10 in the top spot. So I'll do 5 times the first row, but I'll do negative 2 times the second row. And let me go ahead and compute these things. So the first row will become 10, negative 15, 40. And the second row will become negative 10, negative 8, and negative 34. Now I have what I want here. If I add these two rows together, I can wipe out this negative 10 below it. Or if I wanted to, I could add row 2 to row 1 and wipe out this 0. But you'll find that that is not exactly the way you want to go. You want to get comfortable with what I'm about to do and try to mimic it, because all of the theory and all the work we're going to do is going to work in exactly this fashion. So what I'm going to do next then is I will simply add row 1 to row 2. And when I say add row 1 to row 2, leave row 1 be and add it to the second row. So 10 minus 10, that'll give me a 0 into that spot. Negative 15 plus negative 8 will give me negative 23. And then finally 40 minus 34 will give me 6. Now I have the answer for y right now, but it's not quite what I want just yet. Now you can make life a little bit easier on yourself too. Like here, I might, if computations necessitated it, I think that I would divide this row by 5 because it'll make the numbers smaller. So that's what I'm going to do. You do whatever you can to make the computations as easy as possible, and whatever you do, don't rush through these. And also use the notation like this. Instead of saying divide by 5, I'm going to multiply by 1/5. Believe it or not, all of these little things are suggestions that will be useful later on. So the first row will go back to 2, negative 3, slash 8, which was its original at the beginning. The second equation I can't really make easier because the 23 is a prime number, so I can't really do anything about that. And I certainly don't want to divide by negative 23 because it will leave me a fraction, and then I will be dealing with fractions for the rest of the problem. I want to avoid that. It's okay to have fractions at the very last step, but not while you're doing the steps. So now to make this compatible, I'm not going to multiply the second row by 3 and the first row by 23. Instead, what I'm going to do is I will multiply the first row by negative 23. So the first row becomes negative 46. 23 times 3 is 69. 23 times 8 is 184, so I think we're at negative 184. And the second equation I will leave. Second row, I should say, although it is equivalent to an equation, of course. Now I can wipe out the item that is right above here by taking 3 times the second row and then adding it to the first row. So this looks like this: 3R2 plus R1. Now this is the beauty of what we're doing here. This 0 will have no effect on this entry. So that entry is done for the rest of the problem. That's the beauty of getting zeros in these places. Now when you do this, what you ought to do is make sure you just write down the second row and leave it alone, because it's not doing anything here except a multiple of it is being added to the first one. So if I take 3 times R2 plus R1, so 3 times 0 minus 46, we'll leave a negative 46 here. Now I'll be able to wipe this out, since 3 times negative 23 is negative 69 when I add it to row 1. Gone. 3 times 6 is 18. When I add 18 to negative 184, I believe I end up with negative 166. Now I am prepared to do the last step. I don't think you have to write this because I think it's fairly obvious. But what I have right here is, here's the x. This is the coefficient for x after all is said and done. And this is the coefficient for y after all is said and done. What I can do is divide the first row by negative 46. So I can do negative 1/46 R1. And then I could do negative 1 over 23 times R2. So when I do the negative 1 over 46 R1, I'll end up with a 1 here, a 0 here, and then negative 166 over negative 46 gives me 166 over 46, and we saw that that simplified to 83 over 23. On the second one, second row, we get a 0, 1, and then we get negative 6 over 23. So you can see I get the same answers this way, but there's a beautiful thing right here, and it's this diagonal representation. This is the gold standard for solving equations. If I can give you an output like this, then you know what the answer is. So in a way, this course tries to study situations that give us an answer where the left side is like this. We're going to try to get all of our matrices to be like that. Consider if you were a programmer and you wanted to come up with a system that allowed people to be able to read off the answer just by looking at it. Well, that means you would have to get a matrix to this format, and then you could say what x and what y is equal to, but you'd have to make sure the program does this first. Otherwise, there would be extra steps to do. And it depends on the user, of course, but if you wanted the most simple application, you would try to get these ones here. And that's a huge chunk of what the course is about. So we're going to look like, this is what we're going to try to get as we go through. Whatever these stars happen to be will be the answers to the problem. All right, now you should also be aware, besides of getting the answer, of what it actually means. In this, we had 2 lines. The one line was the 2x minus 3y equals 8. So I'm just going to draw a real rough sketch of this situation here. So on the one hand, we had a line that came in like this. That would be 2x minus 3y equals 8. And then we had another one that comes down like this a little bit. And that was the other equation, which was what? 5x plus 4y equals 17. And what we have here is this intersection point right here. That corresponds, or well, that doesn't actually correspond. That actually is the point, 83 3 over 23, comma, negative 6 over 23. So we ended up with a solution because the lines intersected each other. So we can see graphically what the answer to the problem would have been. And you could have used that at the very beginning of the problem. Now, more difficult to graph are problems that involve more equations. So let me do a system of equations that has 3 equations. So let me mark that one off. Let me do another example here. Here we're going to have x plus 2y plus 3z, 4x plus 5y plus 6z, 7x plus 8y minus 9z. Now, it's not a plus 9z because with a plus 9z there's no solution. So I wanted to have one that has a solution, and so I had to change that one number to a negative. And once again, as I go through the problem, watch how I try to avoid nasty little fractions and things like that as I go along. And the advice is that I'm still giving you this advice. Take your time, slowly do each step. You won't believe how hard it is to find an error you've made at the end of the problem. So let me start with our augmented matrix. I have 1, 2, 3, 4, 5, 6, 7, 8, negative 9. And then I've got my vertical bar, 10, 11, and 12. Now what I'm going to try to do is similar to what last time, except I'm going to try to get ones in a diagonal fashion. So I want a 1 here, which is already there, which is nice. But I want a 1 where this 5 is eventually, and I want a 1 where this 9 is eventually, and I want zeros for all of the other entries. That way I want my answers to be displayed so explicitly I can't possibly make a mistake. What we do is start with the first column over here. I'm going to use this one to wipe out the items below it. So the way I can do that is I can take negative 4 times the first row and then add it to the second row. So I'll wipe out the 4 underneath of the 1. Let's go ahead and do that. Well, when you do this, leave row 1 alone. And then let's see what happens to row 2. As I mentioned, negative 4 times 1 is negative 4. Added to 4 is 0. Then we have negative 4 times 2 is negative 8. Added to 5 is negative 3. And then I have negative 4 times 3 is negative 12, plus 6 is negative 6. And don't forget the other side either. Negative 4 times 10 is negative 40, plus 11 is negative 29. Now to wipe out this entry here, this 7 here, I need to multiply this first row by negative 7 and then add it to the third row. So I'll do negative 7r1 plus r3. So you can see there's a bit of efficiency here with this notation. It allows you to stack up multiple steps at one time. So once again, this spot is easy. Now let's do the rest of them. 5 times negative 7 is negative 14. Negative 14 plus 8 is negative 6. 3 times negative 7 is negative 21, plus negative 9 is negative 30. And then finally, let's see, negative 7 times 10 is negative 70, plus 12 is negative 58. Okay, now the way you go about getting the diagonal thing that I'm thinking of is now what I'm going to do is peg this guy right here, this negative 3 right here, and I'm going to use it to wipe out the item above it and the item below it. Notice that when I do that, when I add row 2 to the first row, it can wipe out that entry, putting in a new 0, but notice that 1 will be untouched. Similarly, this 0 down here will be untouched because this entry right here can't do anything. So let's go ahead and do that next. Now, I can multiply the second row by -2 to wipe this entry out. Unfortunately, I don't want to multiply by 3/2 because once you get a fraction, it gets nasty. I can't divide this row by -3 to make it easy on myself because of this 29. It's really not letting me do it. I could divide this last row by, say, -2 and make it a little bit easier, but I really don't see how it's going to save me any time. And after a while, you'll get more comfortable making these decisions. This is, I've been doing this for a long time, so I have sort of a strategy in my mind. So with that in mind, what I'm going to do is make it so that this is an easy number to wipe out. So I'm going to multiply the first row by 3. So I'm just going to go 3 times R1. Nothing else will change. So I have 3, 6, 9, 30, and the other rows I'm not touching. Okay, next, now I'm ready to do it. So if I do 2 times row 2 and add it to row 1, I'll wipe this 6 out. And once again, this 3 here will be untouched. Eek. That was a mistake. Now the other ones, be careful here. So 2 times -6 is -12, plus 9 will be -3. And then 2 times -29 is -58, plus 30 will be -28. And of course the second row, leave it alone. And the third row then, I will take -2 times the second row and add it to the third row. That will wipe this -6 away. And once again, the first entry is untouched. That's the whole reason for this, is that you're making the list of equations smaller and smaller and smaller, so that until you eventually get to the diagonal that I was suggesting. Of course, it's a 0 there. All right, -2 times -6 is positive 12. Positive 12 plus -30 is -18. And -2 times -29 is positive 58 plus -50. Oh, that's beautiful. Look at that. Now this is strictly for convenience right now. I'm going to do this. I'm going to take -1/18 times row 3. So notice my diagonal is starting to come into play here. You can see it. Now what I'm going to do is use this 1. And whenever you can get a 1, that's the best thing that you can get. I can use this 1 to wipe out the entries above it, and then I will have the diagonal I've been talking about. So I can take 3 times the third row and add it to the first to wipe that entry away. And if you want, if it makes life easier for you, write the third row, since you're not going to change anything there anyways. Now notice this 0 doesn't do anything to that 3. This 0 doesn't do anything to that 0. And finally, 3 times 1 is positive 3. When I add it to that, it zeroes it out. Another beautiful thing here is I noticed that if I take 3 times 0 and add it to this, it doesn't change this value at all. So in fact, no matter what I do, I'm not going to change that either. Now, this time I want to multiply by positive 6 to wipe that entry out. So I'll take 6R3 plus R2. And once again, that 0 here doesn't do anything to this down 0 at the bottom. I'm sorry, 0 here doesn't do anything here. This 0 here doesn't do anything here. But 6 times 1 is 6. That wipes that out. And I've almost got the diagonal that I want. The very last step is to multiply by what you need to get 1s. So I'll do 1/3 R1, and I'll do negative 1/3 R2. So I have 1, 0, 0 slash negative 28 over 3. Now I have 0, 1, 0, 29 over 3. And then 0, 0, 1, 0. And so now I have my answer. Let me check. Good, it checks out. So my answer then, I have x, y, z equals negative 28 over 3, 29 over 3, and 0. Now, in case you're wondering exactly what this might look like, it's difficult to draw it, but I will try the best I can. What we have here is we have a plane, and another plane intersects it. Now this part's not so bad. I can handle all this, right? However, then when I put in a third plane, it has to intersect in just a perfect way, something like this. So let me have another plane come and see if I can make it vertical. It's very difficult to draw this and make any sense of it. Even the thing in the book doesn't look good to me. But what you see here is that the first two planes intersected in this line, and then the third plane intersected just so perfectly that they intersected in a point. And that point in a three-dimensional coordinate system is, as you might expect, negative 28 over 3, 29 over 3, and 0. It's extremely difficult to draw, but at least you can understand the nature of the solution. So it does have a visual solution. In this course, we don't have any problem expanding this, going to 4 equations or 5 equations or 6, or even to an unknown number of equations. In situations like that, we won't be able to graph the solutions. So you won't always have these pictures to deal with. That introduces a level of abstraction that you may not have been familiar with from before. But such is the nature of this course. It's more theoretical than other courses that you've had. There's plenty of computation, as you've seen, but there's also a requirement that you understand the inner workings in a deeper level than you ever have had to before. So let's talk about some of the stuff that we did here. All the things that I did are called elementary row operations. And let me tell you what we did. One of the things we did is we add a multiple of one row to another row. And I think, what else did we do? We could multiply any row by a non-zero number, so we multiplied. And one thing I did not do was, this last one is to swap two rows. When you swap two rows, it's usually to try to get an item into the correct location on the diagonal. So if, for example, this might come in handy if you end up with a situation like the following. I don't know what these are. Let's say you ended up with something like this. You might swap rows 2 and 3 so that you can get it in the correct visual display. So you might think of these, I don't know, one, some people just call it replacement. Two, to multiply a row by a non-zero number is to scale it. And then part 3, we'll just say swap. And whenever you have a system of 3 equations, you have any kind of, well, not just a system of 3 equations, a system of equations in general. So I should be a little more specific about that. A system of linear equations. There are 3 possible outcomes. So one possible outcome that you could have is a solution. A single, unique solution. So when you have a point or something, like in some of those where the 3 planes intersected in a single point, or where the 2 lines intersected in a point. So that can happen. You could have an infinite number of solutions. Or the last thing that can happen is no solution. Let's take a look at lines. In the case of lines, so for lines, this is 2-dimensional. All we have is up and down and left and right. For that, we either have we have something like this where they would intersect in a point. So there would be a single solution. Or a unique solution. That's the preferred term of the book. You could have this where they are actually the same line, and that's an infinite number of solutions. And then, of course, you could have something like this last case, parallel lines. And there would be no solution. There's no intersection at all. In 3 dimensions, it's harder to draw the pictures, but like you saw where we had one solution, it's the intersection in a point of 3 planes. If the planes somehow intersect in, say, just a line, you'll have an infinite number of solutions. So, for instance, if 2 planes are actually the same plane and the third plane is practically anything else, they'll intersect in a line. And then the no solution case, you could have 3 parallel planes. You could have 2 planes that intersect, but one that intersects not along the line of the other 2 intersection points. So you can have something like that happen. All sorts of things. There's more possibilities to not have a solution than I could possibly list all of them, or at least would want to list all of them for you, because there's a lot of different possibilities. But I think you get the idea. Let's do some more examples to get more comfortable. Here we have x minus 3y plus 4z equals -4. 3x minus 7y plus 7z equals -8. And -4x plus 6y minus z equals 7. So once again, I'm going to go with the augmented matrix. Oh, once again, it's set up nicely. I can use this one up here to wipe out the element, the numbers underneath of it. So I will take negative 3r1 plus r2. And when I do that, I know I wiped that number out. So let's see what else we have. Negative 3 times negative 3 is positive 9. Positive 9 minus 7 is 2. And then negative 3 times 4 is negative 12. Plus 7 is 5. And then finally, 12 minus 8 is 4, positive 4. Now let me work on that negative 4 down there in the corner. So I will multiply the first row by positive 4 and add it to the third row. So 4r1 plus r3. And I know I get a 0 here. So 4 times negative 3 is negative 12. Plus 6 is negative 6. Then what do we have here? 4 times 4 is 16, minus 1 is 15. Negative 12 plus 7 is negative 5. See what I mean? And then if I were to go several steps later, I would never know that I did that. It would take a while to hunt and find it. I did these beforehand, so I know when something seems up. Now on the very last one, then we have negative 16 plus 7 is negative 9. Now notice here, we have a nice thing. I can use this 2 to wipe out that negative 6. Unfortunately, I can't take out the negative 3 as easily. So I'm going to multiply the first row by 2 and not do anything to anything else. I really urge you not to do too many steps at one time. There'll be a lot of, because you'll get bored doing it and you may get anxious to make it go faster, but I urge you, don't do it. And then the rest are the same. Now I can use this 2 here to wipe the stuff out above it and below it. And that's 3r1, that's 3r2 plus r1, and that's 3r2 plus r3. So once again, this is safe. Since I'm using R2 to do things, I can go ahead and write it and just leave it be. And nothing happens there. Of course, I know above and below it I get zeros. Now let's see what we have here. 3r2 plus r1. 3r2 plus 3 times negative 5 is negative 15. Plus 8 is a 7. And then I have 3 times 4 is 12, minus 8 is positive 4. And then down here I have negative 5 times 3 is negative 15. Oh, look at this, it wiped out those two. And then 3 times 4 is 12, plus negative 9 is 3. We can stop right now, because we know there is no solution. Why? Look at the third row, this row right down here. Look what it says. This row says 0x plus 0y plus 0z is equal to 3. In other words, 0 equals 3. That can't happen. That's what they call a logical fallacy. So once you get to a logical fallacy, you can stop the presses. It's all set. It's all done. There's no solution once we see something like that. Now, if it might have been, if this had been a 0 here, that 3 had been a 0, then that would have been okay, because that wouldn't have been a logical fallacy. 0 equals 0 is a fine equation, but 0 equals 3 is not. So our answer is no solution. That's part of what I want to do some of this for, so that you can see when something strange comes up other than just a solution. And that's one thing about this course. When you're done with it, you will have a full understanding, a deep understanding of what all these things mean by the end of the course. So let's solve another one. We have 2x plus 4y minus a z equals 8. 3x plus y plus 5z equals 9. Negative 8x minus 16y plus 4z equals negative 32. And as with all the other ones, I'm going to go ahead and rewrite it as an augmented matrix. And I'll start to work it here. Now I see right off the bat, I like the way 2 can wipe out the negative 8. That's nice, but 2 cannot wipe out the 3. So I'm going to multiply the second row by 2. Now you think about it, probably been easy to divide this whole row by negative 8 and then swap it and put it in a first slot, but it's not going to be that big of a deal anyways. Now I'll start to take this 2 and wipe out what is underneath of it. So to wipe out this 6, I need to multiply 2 by negative 3. So I'll do negative 3r1 plus r2. So I'll get a 0 there. Now let's see what happens here. Negative 3 times 4 is negative 12, plus the 2 gives us negative 10. And then 3 plus 10 gives us 13. And then negative 24 plus 18 is negative 6. And then to wipe this out down here, I've got to multiply the first row by 4. So 4r1 plus r3, put a 0 in there. 4 times 4 is 16, minus 16 will be 0. A little more in just that one shot there. And then finally, negative 4 plus 4 is 0. Oh, we got another specialized problem here. 8 times 4 is 32, minus 32 is 0. Now, we can also stop. We're not going to do anything more with it just yet, not till the next section. We can stop here for now. Now we have an infinite number of solutions. Let me go back for a second. If I look at this first row, by the way, if you haven't had Calculus 3, you may not know this, but each of these equations is a plane when you graph them in three-dimensional space. So the first equation is a plane, the second equation is a plane, and the third equation is a plane. So it's whether these three planes are going to intersect or not. Well, if I look at this third row, if I did divide it by negative 4, say, I noticed that it would be exactly the first plane. So what we have is a situation like this. We have two planes are the same thing. So it's kind of like having one line. But then another plane comes in here and intersects it. How it does it doesn't really matter. I really don't care about that part of it, but I can see. I could even make it a little bit easier there if I throw those things in there so you can see which one's which. But here then, you can see that the total intersection of the three planes is a line, and there's an infinite number of points on that line. So that's why there's an infinite number of solutions. We're not doing anything with it just yet. We just want you to recognize when stuff like that pops up. We'll go into more detail later. Right now, this is just to get you started. This leads me to a definition. A system of equations. Well, let's be careful here. I shouldn't say a system of equations. What we're dealing with here are linear equations. None of this stuff would be true for equations in general because the lines don't have to be lines, they can be curvy. So a system of linear equations is called consistent. If it has at least one solution. So this takes care of the situations here where a unique solution, where they all intersected at a point, or an infinite number of solutions. So it's consistent of those. If either one of those things happens, the system is inconsistent when there's no solution. So we'll keep in mind, what we're going to do in the course is try to keep a track of augmented matrices when they have solutions and when they don't have solutions and things like this. This will be useful later on when we're trying to categorize things. So let's show you a little touch or a little bit of how this course is a little heavier than your usual course. And you'll see right now. So let's do an example. Determine the value, or values, it could be plural, of H that makes the system of equations consistent. So, well, actually, I'm not giving you a system of equations. I'm already going to give it to you in augmented matrix form. As with anything else, if you want to figure out what's going to happen, just start doing elementary row operations. So, like before, I'm going to use this one to wipe out the number underneath of it, and we'll just see what happens. So all I have to do for that is to multiply the first row by 2 and add it to the second row. So if I do 2 times h, I'll get 2h and add it to 4. I can't do much of anything but call it 2h plus 4. And then, oh, well, this side's okay. Well, now, this here is nice, because no matter what h is, if this spot is not 0, then my answer for y will be 0. If I have nothing here, then I still have an answer. So let's take a look at this way. So if 2h plus 4 does not equal 0, then y equals 0, and we have a solution. Why do we have a solution? Because once you have the y, because if this is not 0, I can divide by it, and then I'll get a 1 right here and a 0 here. So I'll have the y value. But then if y is equal to 0, then this first equation will be x plus hy equals -3. But that y is 0, so I'll know that x is equal to -3. So I'll have a solution there. On the other hand, if 2h plus 4 equals 0, we have the following. And this is okay as well. This then is a single line. The line is x plus hy equals -3. It doesn't matter, even if h is 0, you'll have a vertical line x equals -3. For any other thing of h, you'll be able to solve for y, get it in slope-intercept form, and you can see that will also be a line. You'll have an infinite number of solutions in that case. So either way, so this is an infinite number of solutions. So no matter what, we have at least one solution. So the system is consistent no matter what. So I already said no matter what. So it doesn't matter what h is, the system is consistent. So problems like that are the things that we're going to be having. Let's try another one of these things to show you how weirdly complicated these things can get. Sometimes when you sit and think about these things, because there's so many different points or so many different numbers in all these different places, your mind may have trouble until you actually sit down and do it by hand. Trying to do these in your head can be very difficult. Let's try this again. So determine the value or values of h that makes the system consistent. So here we try again. Here I have 2, -3, -6, 9. Then I have an h and a 5. So I'm going to be able to wipe out the second row, the whole thing actually, most of it at least, by simply taking 3 times the first row and adding it to the second row. So I'll get a 0, I'll get a 0, and then on the other side I'll have 3h plus 5. Now if I want this row to be, consistent, what I need is for this to equal 0. I need 3h plus 5 to equal 0. That way I'll have a row of zeros at the end. That is, in fact, the value of h that will make the system consistent. Now, as I speak, and I should do this, a lot of people, when you use certain words, you take for granted their meaning. But when I talk about rows, I'm talking about this way. These are rows, and then columns are this way. So as we go through the course, we'll be talking about rows and columns all the time, and coming up with different theorems and whatnot that will relate rows and columns to solutions and things of that nature. But also, some notation that we also have goes like this. If I have something like this, this has 2 rows, 3 columns. I keep forgetting the N in there. My pen does not want to write them. So what we say is the size is 2 by 3. So when we list the size, we list it as rows by columns. And I'm using the X is nothing but a placement for the word by. So if you have something like this, the size of that thing equals 3 rows by 1 column. Even you can have something like this. Here the size is 1 by 1. And when you see this here, this is no different than just a plain old number. But sometimes these things dissolve all the way down to a 1 by 1 matrix. Now let's look a little deeper. Let's keep small in our size, but look at this. Suppose I have the following equations. AX plus BY equals F. That F's a number, not a function. CX plus DY equals G. And here's all I'm telling you about these numbers. I'm not going to tell you a lot about them, but I do know that none of the A, B, C's, or D's are equal to 0. So let me convert this to an augmented matrix. Like so. Now, I don't know anything about A and C. I don't want to multiply by 1 over A. I don't want to play with fractions. I'm going to do just like I did before. So I'm going to multiply the first row by C and the second row by negative A. So the first row will be AC, BC, FC. And the second row will be negative AC, negative AD, negative AG. Now let's add row 1 to row 2. Now we have a couple of ways to have a solution here. Now the system is consistent if one of two things happens. We could have FC minus AG equals 0, but BC minus AD does not equal 0. That way I'll be able to tell that y is equal to 0, because what I'll be able to do, remember, we get this equation here in the second piece. I'll have a solution. If this is not 0, I can divide by it and then get the value of y. So there's one thing that could happen, or that's not the only thing. We could have BC minus AD. If that equals 0, then we also need the FC minus AG to equal 0, because that'll give a row of zeros, and we already know that has a solution. The first row, since these are non-zeros, is going to be a line. So you have that possibly. Or what else could possibly happen here? What if this piece was 0, but this was not 0, then you would not have that. So if I try to go BC minus AD equals 0, but FC minus AG does not equal 0, no. So we have these situations then. One of these two things has to happen. Oh, there's also one other thing I guess I should mention. The last easiest thing is the following. Let's leave this and let me take this out. The reason why is because no matter what, if this is not equal to 0, then no matter what, if it's attached to y, I can divide by it. And even if this number is 0 or not 0, I will still get an answer. So I didn't need that little piece there. These are the only situations that will give me consistency. So these are the types of questions that we're going to be looking at. You can see it requires a little bit of thought. One last example. Check this out. What I have here is an augmented matrix. And what I want to do is a single row operation. I would like to take this number 1 here and wipe that 4 out. So we've seen this a couple times already now. So I will take negative 4R1 and add it to R3. And let me put R1, and since I also put R2 since I didn't do anything there. Okay, so let's see here. Negative 4 times negative 2 is positive 8, minus 1 is a 7. Negative 4 times 1 is negative 4, plus 3 is negative 1. Of course, the 0 didn't do anything over there. It left it alone as a negative 6. Now check this step out. Now let me start from this guy here. Just for practice, I want to take this matrix and put it back to the way it was originally. That means I want to put a 4 back there. So if I want to put a 4 back in that spot, I can go 4R1 plus R3. Now let's see the way the rest of it shakes out. I didn't do anything with the second row in this one step, so let me leave it. But actually, I made a mistake. No, I'm good. So now let's see. 4 times negative 2 is negative 8, plus 7 is negative 1. And then we have 4 times 1 will be 4, minus 1 will be 3. And then the 0 doesn't do anything there. Look at this matrix that I ended up with. 1, 0, 4, negative 2, 5, negative 1, 1, negative 2, 3. Look at these numbers, exactly the same. Even this side is the same. So what I'm getting at is I was able to take a row operation and take its inverse. So negative 4R1 plus 3 is the inverse of 4R1 plus R3. So you can undo a row operation. You can reverse it. So these are inverses of each other. If you multiply a row by a non-zero number, well, to reverse that, you can simply multiply by 1 over that number. If you swap 2 rows, to undo that, just swap them back. So all of the elementary row operations have inverses. And what we'll do next time is we will delve deeper into some of the steps that we use to solve things. And what you're going to want to do from the very beginning is to keep very good notes, because all the things I just said, every little step in detail, will be used in proofs and theorems later on, and you'll be required to know those steps. Keep that in mind.